Hi everybody, part 3, collisions in one dimension. A collision is an interaction between two or more objects, in which a force acts on an object for a period of time. In other words, the collision provides an impulse to each object. Collisions can be classified as elastic or inelastic. An elastic collision is a collision in which both kinetic energy and momentum are conserved, which is to say that they are the same before and after the collision. So let's say that a little longer. Kinetic energy is the same before and after the collision, and momentum is the same before and after the collision, the total momentum and the total kinetic energy. Okay, an inelastic collision, on the other hand, is a collision in which the momentum is conserved, so the momentum is the same before and after the collision, but the kinetic energy is not. No collision at the macroscopic level is perfectly elastic. Macroscopic means like kind of real life, bigger, like cars and you and that kind of stuff. Okay? Perfectly elastic collisions only occur at the atomic and subatomic levels. This is because collisions at the macroscopic level, so our level, big, involve losing energy to sound, distortion, like change in shape, like you can think of the cars colliding and they dent and stuff like that. And that distortion creates thermal energy or heat. Okay, so there's always energy lost in kind of big collisions. Okay, again, at the macroscopic level, like two electrons or a proton and an electron running into each other, those are more elastic, okay, whereas the kinetic energy is the same. Here, most of our collisions are going to be inelastic, and I'll show you how to prove that shortly. Okay, so before we do that, let's just some more notes. Okay, so we are right here. Okay, so a group of two or more objects that interact is called a system. Okay, this is, again, physics 20-ish stuff, but let's talk about it. In the context of momentum, when the mass of the system is constant and no external force acts on the system, we say the system is isolated. This is a key concept to developing strategies for collision. Okay, our system has to be isolated. No energy in, no energy out. Okay, no mass comes in, no mass goes out. Okay. So, the law of conservation of momentum states, in an isolated system, okay, so again, constant mass, no external force, the total momentum of all the objects before the collision is equal to the total momentum after the collision. Mathematically, this is shown as P before equals P after. Momentum before equals momentum after. Okay, easy. We can use this law to solve collision problems. In order to do the necessary calculations, we classify these interactions or these collisions as follows. All right, flip the page. So, linear interactions, so that means that all of the motion for all the objects, everything moves back and forth in a straight line. Okay, so everything moves back and forth in a straight line. Okay, now, these collisions, these linear interactions, have collisions in when the objects collide and bounce apart. So they collide and don't stick together. Then, of course, you have collisions in which they hit each other, do stick together, and move off in a certain direction. Okay, and then you also have explosion-type reactions, collisions. Okay, even though we don't think of an explosion as a collision, it kind of is because the momentum before has to be the same as the momentum after. Okay, then of course we have two-dimensional collisions. Okay, and we have intersection collisions. Okay, so one thing is going this way, one thing is going that way, and then they'll move off kind of that way-ish. Okay, then we have glancing collisions, which are things like this. Okay, they come across, and then one, as they hit, one goes this way and one goes that way. Okay, and then we also have explosions for two-dimensionals. Okay, our focus right now is the linear interactions. Okay, so special considerations. When dealing with momentum in collisions, Lucky us, we don't have to convert kilometers per hour to meters per second. This is because the units of velocity will cancel out or can be solved in kilometers per hour. So we don't need to do that whole divide by 3.6 thing for most of this. However, this is only true when dealing with before and after cases of a collision. As soon as energy creeps in, remember kinetic energy is 1/2 mv squared. Oh boy. As soon as that creeps into the calculations or the questions, now we have to convert the kilometers per hour to meters per second for the energy calculations to work. Grr. Okay, so anyways, we'll do some of that. Okay, remember that direction always counts. Momentum is a vector quantity. So west and south are considered negative, north and east are considered positive. Okay, so let's look through some of the examples because I find that it's easier to learn this stuff by watching some examples. They're not hard, but there's some key concepts here that you need to put together. All right, so let's look at a collision when objects do not stick together. Okay, number one. A 0.25 kilogram steel ball is traveling east at a velocity of 4.5 meters per second when it collides head-on with a 0.30 kilogram steel ball traveling west at a velocity of 5.0 meters per second. After collision, the 0.25 kilogram ball is traveling west at a velocity of 2.0 meters per second. What is the velocity of the 0.30 kilogram ball after the collision? Oh, that's a lot of words. So let's see if we can sort this out. We are going to start all collision problems with this. Momentum before equals momentum after. Okay, we start there. Okay, now, sometimes you can see some textbooks use that symbol. So the sum of the momentum before equals the sum of the momentum after. That's just, it makes things more complicated. So okay, momentum before equals momentum after. Good. Now, let's talk about what's going on. I have that much steel ball moving at a velocity. Okay, so he's got some momentum. Momentum equals mv. Okay, and it collides on with another ball moving at another velocity. So it's got its own mv. So there's two things interacting beforehand. So I've got two momentums. Okay, now I can expand this out. I can say momentum 1 plus momentum 2 equal. Okay, so I have one mass beforehand, okay, having a velocity. So let's call that v1. There's another mass with another velocity. Now there's only two things moving, so that's good. So there's two things before, then there's the equal sign. Now I have momentum after. I've got two objects moving after the collision. After the collision, this guy is moving with that, and I'm trying to find the velocity of the third one. Remember, these do not stick together, so they are completely separate. So I have mass 1 moving at a different velocity. So let's call that mass or velocity 3. Okay? Plus the second mass moving at a completely different velocity. So let's call that velocity 4. Wow, there's a lot of little numbers there, hey? Okay, big thing. Two things moving before, two things moving after. Awesome. Okay, so let's see. That first thing moving, 0.25 kilograms, moving east. East is positive, so that is moving at 4.5 meters per second. Plus, now the second thing moving, that's the 0.3. 0.30 kilograms. Now he's moving west. Ooh, west is negative. Okay, so that is negative 5.0 meters per second. Okay, that's important. Okay, because if I just said positive 5.0, that's not good. Okay, one of them's moving east, one's moving west. This guy has a negative momentum. This guy has a positive momentum. Positive speed, negative speed. Like, we've got to think of it that way. So, tell you what, let's let's play with that for a minute. Okay. So before the collision, so 0.25 times 4.5 plus 0.3 times negative 5. So let's just forget about sig digs for just a minute. The total sum of the momentum of the whole system beforehand is negative 0.375 kilograms meters per second. So that is how much momentum we have before the collision. Well, that means that I have to have a sum of negative 0.375 kilograms meters per second after the collision. Okay, that's a big deal. The momentums have to be the same. So let's just have a quick look at this. So we have our second mass, so that's 0.25 kilograms again. Now after the collision, the 0.25 is traveling west. So again, that's negative at 2.0. So negative 2.0 meters per second. Plus, okay, we have our third mass, so 0.30 kilograms, moving at some velocity that I don't know. Now, I could say V4, or I could just leave the V there now because that's the only variable. Okay, it really doesn't matter. Now, okay, all good. So let's have a look at this. So 0.25 times negative 2. So this is negative 0.5. Okay, plus 0.30 kilograms times V. Now look, when we get better at this, we won't even need to do this step. We'll just be able to figure everything out, and then you can go formula, substitution, answer. So V equals. I'm not sure we're there yet for the first time you've ever done one of these. Now, if you did take Science 20, you did do some of this stuff, but if you did, it's probably a long time ago. So anyways, so look at what I've got going on here. Negative 0.375, negative 0.5, and then 0.3. So there's some algebra going on here. So this is negative 0.5. So then I've got to go positive, like add 0.5 plus 0.5. Okay, so negative 3.75 plus 0.5. Okay, so that is 0.125. And again, we can put the units on now if I really want. Kilograms, meters per second. Now, it is positive. So this part canceled, so you have 0.30 kilograms times V. So divide by 0.30, divide by 0.30, divide by 0.3. Okay, so that works out to, now my calculator says 0.416666 repeating. Okay, remember we have to use all our digits. Okay, so we haven't used any really complicated numbers yet, so using all your digits is fine. If you have a TI Inspire, you can scroll up. If you have one of the new TI 84s, you can also scroll up and pick those answers. If you have an old 84 or a TI 83 Plus still, because they're still around, if you have one of the older operating systems, then we've got to work on storing numbers. Ask your teacher about that. I will show you a little more when it becomes more prevalent in the next section. But anyways, for right now, 0.125, 0.3. Okay, so there's only 2 sig digs here, so our velocity is 0.42. We have 2 sig digs meters per second. Now, I need you to notice something about that. That is a positive number, which means this velocity, so look up here, we had one momentum. The first object was going east, the second object was going west. After the collision, the 0.25 is going west. That's where the negative 2 comes from. And then the 0.30 is going east. It's going positive 0.42. Okay, so really we can interpret this as being the velocity is 0.42 meters per second east. Wow, that was intense. Okay, so we'll try another one of those here, well, in a second. We've got to do part B still, but that's how you do these ones. All right, then part B says, is the collision elastic or inelastic? Now remember how we do that, or what the idea is elastic collisions, energy is conserved. So the energy of all the objects before the collision is the same as all the objects, or the energy of all the objects after collision. So what we can do is, oops, pencil. So EK before has to be EK after. Okay, and if it is, then it's elastic. If it isn't, it's inelastic. Now remember, these are at the macroscopic level. Like you can see a 0.25 kilogram object. It's like a ball, like I don't know, like a tennis ball or something like that. You can see it. So this collision will most likely be inelastic. Okay, but you can't just say that. You have to prove it. Okay, and how we do that is we figure out the kinetic energies of everything before and everything after. So remember, there was two objects moving before, so we have a 1/2 m1 v1 squared. Okay, 1/2 mv squared plus, okay, we have another 1/2 mv squared, but this is for mass 2 going at that velocity 2. Now remember, energy is not a vector, so direction doesn't count here, but what happens, the mathematics plays that out. It's beautiful. So just bear with me. Okay, now after the collision, remember there's still two things moving. So you have 1/2 m1, we called that v3 squared, plus a 1/2 m2. The second object is still moving, but that was at like v4 squared. Put those in brackets if you really want. Not too worried about it. But look what happens. Okay, so 1/2 times 0.25 kilograms. Okay, now the first velocity, that was 4.5 meters per second. Meters per second squared. Now, the second one is 0.30 kilograms times, now technically it's negative 5.0 meters per second squared. But guys, what is negative 5 squared? Well, this one is easy. It's positive 25. The 25 isn't so as important as the negative squared is going to give you a positive number. So really, we don't even have to worry about the negatives in terms of energies, because energy, again, is not a vector. Regardless. Okay, if you put the negative in, as long as you put it in brackets, your calculator will take care of it. So let's figure out how much energy, how much kinetic energy we have in this reaction before the collision. So 0.5 times 0.25 times 4.5 squared plus 0.5 times 0.3 times bracket negative 5.0, close the bracket, squared. Okay, even if you put the negative in just like I have it here. Okay, and that works out to, and then we have 2 sig dig, so 6.3 joules. Positive. And again, that makes sense because that negative squared turns out to be a positive. So I've got 6.3 joules of energy before the collision. Okay, awesome. Now, let's do the same thing for the second part. So I've got 1/2 0.25 kilograms. Now that guy, remember, he was moving at negative 2.0 meters per second squared. So he was 2.0 meters per second west. So that's why I put the negative in. Now again, you don't need the negative here because the squared is going to take care of it. But again, I just want to show the point. Okay, so then we have the 0.30 kilogram thing. And that's what I just figured out, 0.42 meters per second. And then I got to square that. Now, remember, you have to use all your digits. This was 0.416666. Repeating, okay, and you can just scroll up on most of your guys' calculators. You can scroll up and pick that whole number off your calculator and use it. Okay, great. So let's just have a quick look at what this is. So we go 0.5 times 0.25 times bracket negative 2.0 bracket squared plus 0.5 times 0.3 times Now I'm going to scroll up. Now here, I'm going to show you guys something here. Okay, so I'm going to click that off. So you can see, then I'll use my camera feature. All right, there's my calculator. Okay, let everything get into focus. So then if I just scroll up, so I can pull that number, highlight it, and hit enter, bring it down, and then go squared. Okay, so you need all those digits. Okay, awesome. So that's how that one works. If you have an older TI-84 or 83, you might just have to type those for now. I'm going to show you how to store those in a minute. Hopefully you already know that from Physics 20, but again, I didn't teach you Physics 20, so I don't know. Anyways, I'm going to go back there. So there's squared. Oh, I might as well hit enter while we're here. Look at that, 0.526. So 2 sig digs is 0.53. So here we'll go back to this guy. So that is 0.53 joules. Now, you don't have to be amazing at this yet to figure out that those two numbers are not the same. So how we show that, if it was elastic, they would be the same. So the thing is, they are clearly not the same. So we put a little strike through that equal sign. They are not the same. And we say the collision is inelastic. Okay. Now, sometimes we might have to take those two numbers and say how much energy was lost. So you take those two numbers and subtract them. Okay. And some of the other times it says, where does the energy go? So if it says that ever, so we say the collision is inelastic and energy was lost. When things collide, you usually hear something. To sound. Okay. Often things the objects are deformed or squish a little bit. Sometimes they aren't, but even if they aren't deformed, that deformation is translated into heat. So we lose energy to sound and heat. And that covers pretty much all the bases for us. Okay, so the collision is inelastic and energy is lost to sound and heat. So in this case, all we had to do was say the energy is elastic. Every now and then, we might have to do that next part. Okay, not a big deal. Whew, crazy. Wow, that was just the first one. There's only 3, so yay, but still, that's okay. Number 2, collisions when objects stick together. Okay, so here's what's going to happen. Okay, we get a car going this way, colliding with another car going that way. And what's going to happen, so that's before, and then after, these two things are going to stick together. So we're going to get some big mass of cars squished and stuck together, and they're going to move off in some velocity. So I don't know, that way or that way. Well, sorry. These are linear interactions for now, so they are going to move straight this way or straight that way. We don't know yet, but we're going to figure it out. And you'll actually find that these aren't so bad once you get the gist of it. All right, so let's have a quick look. A 1.1 times 10 to the 3 kilogram car is traveling east at a velocity of 25 kilometers per hour and collides head-on with a 1.3 times 10 to the 3 kilogram car traveling west at a velocity of 15 kilometers per hour. During the collision, the two cars lock together. What is the velocity of the locked cars as they move together immediately after collision? Now, the wording of this is important because it says immediately after. Because the thing is, as soon as they hit each other, they move off, and then, of course, friction, their tires are still on the road, or maybe they flipped over and are scraping across the road. Either way, they're slowing down, right? So the wording of this is always immediately after the collision before any other frictional forces come into play. That's part of the isolated system bit. Okay, so we're still going to start with P before equals P after. We have to. Okay, that's how we do these things. So before the collision, how many things are moving? Well, 2. So I've got a mass of one thing and a velocity of a second, mass of one thing and a velocity of one thing, and a mass of the second thing plus a velocity of the second thing. Okay, now the two objects stick together. So after the collision, they weigh mass 1 plus mass 2. See, they are stuck together. So in this case, it's going to be 2.4 times 10 to the 3, right? You just add the masses. We'll get to that in a minute. And because they're stuck together, they only have one velocity between them. So we can call that V3. I'm hoping that this makes sense to you, right? Two things moving before, each of them have momentum, m1v1 plus m2v2. After the collision, they stick together, so one big mass in the brackets, mass 1 plus mass 2, okay, moving off at some other velocity. All right, so let's do some math and figure some stuff out. The first mass, now notice how I get a little wider. That's because I just need the room. I know I'm going to need the room because my writing is pretty big on this screen. So 1.1 times 10 to the 3 kilograms. Now it's moving, remember that note we had at the beginning of this? I don't have to convert kilometers per hour, at least not yet anyways. Okay, so I'm just going to say 25 and moving east, so that is positive kilometers per hour, plus mass 2, 1.3 times 10 to the 3 kilograms, times my traveling west, so that is negative 15 kilometers per hour. See how I got fairly big writing because my tablet doesn't let me write smaller. Okay, anyways, so this one is 1.1 times 10 to the 3 kilograms plus 1.3 times 10 to the 3 kilograms, which of course, like I said, is 2.4 times 10 to the 3, but we'll get there. Okay, times V3. All right, so let's just do some algebra and figure this out. Okay, so let's figure out the before the collision part. So 1.1 times 10 to the 3, 1e3 times 25, plus 1.3 times 10 to the 3 times negative 15. That negative is really important, okay? And that works out to 8,000. So, and positive 8,000. Now this is kilograms, kilometers per hour. Now look, I know that there's only 2 sig digs here, so we could be 8.0 times 10 to the 3. I'm not worried about, you don't even need to show this part. You can go V3 equals and just give me an answer. But I wanted to show you the algebra just once because it's kind of a big deal. Okay, so 1.1 times 10 to the 3 plus 1.3 times 10 to the 3, like I said, was 2.4 times 10 to the 3 kilograms times V3. So we're going to divide by this, so 2.4 times 10 to the 3 kilograms, divide by 2.4 times 10 to the 3 kilograms. Okay, look, the kilograms cancel, so look, our velocity for this is still going to be in kilometers per hour. Oh, well that's nice. So anyways, velocity 3 is 3.3 kilometers per hour. And you'll notice that it's positive, so that means this thing heads off in the easterly direction. See up in my picture, I'm right here, guys. Okay, it ends up going east because of that positive number. Okay, so we can rewrite that, or see if it was negative 3.3, then I would probably rewrite it as V3 equals 3.3 kilometers per hour west. But because it's positive, I can just put the word east in the back here and don't have to rewrite it again. So 3.3 kilometers per hour east. That's interesting. Okay, so that's that one. And then it says, here's the kicker. Is the collision elastic or inelastic? Well, look, we already know that it's inelastic. This is macroscopic. The cars are going to make a sound when they hit. They're going to break some glass. They're going to bend together. So we know it's inelastic, but we have to prove it. Okay, so again, we go energy before equals energy after. Okay, and we know it's not going to be, but we don't get to put that in because we have to be sure. What if it is elastic? Crazy. Anyways, so how many things are moving beforehand? 2. So I've got a 1/2 mv squared. That's the first one, so m1v1, plus a second one, so m2v2. Okay, and then afterwards, I'm going to have a 1/2. Now we have that big mass, m1 plus m2, moving at some velocity 3 squared. Awesome. Okay, very, very cool. Now, the only trick here is, remember I told you, as soon as energy creeps in, now we've got to change things to meters per second. So, okay, let's go back up here. The first one was 25 kilometers per hour. Okay, remember I told you earlier we can divide by 3.6, and that gets us our meters per second. So 25 divided by 3.6. So that is 6.94444. Okay, remember we have to use all those digits. Okay, meters per second. Okay, then we go, the next one was 15 kilometers per hour, divided by 3.6. So 15 divided by 3.6. So that's 4.16666 meters per second. And then, of course, that 3.3 kilometers per hour divided by 3.6. Now remember, that's not 3.3. That is, let's see, 3. So we scroll up on our calculator and we pick up all those digits, and it's 3.3 repeating. So on our calculator, we just scroll up to the 3.3, okay, and divide by 3.6. Again, if you have an older calculator, you can just type in 3 and then just like 6 or 7 threes. Okay, it'll be good enough for now. I'll show you a better way next section. But 3.333333333 divided by 3.6. Okay, and that is 0.925 whatever. Okay, so I guess 925.926 meters per second. Okay, so again, you're going to use all those decimals or just scroll up and pick them off. Okay, so this guy here, 1/2 times 1.1 times 10 to the 3 kilograms times 6.94444. Make sure you get all those decimals. So meters per second squared plus 1/2 times 1.3 times 10 to the 3 kilograms. 1.3. Okay, and that was times 4.166666. So really we could write down 4.2 because that's the sig digs. 4.2 meters per second squared. Okay, and that's supposed to equal 1/2. And then the m1 plus m2, that again is the 2.4 times 10 to the 3 kilograms. Okay, times the 0.925. Okay, really we should be writing these down in sig dig, so 9.3 meters per second squared. Again, we're going to use all those digits. Okay, and now when we type these in, this part, okay, so 1/2 times 1.1 times 10 to the 3 times 6.9. You know what, I should show you guys this. Just in case. You know, forgive me because you probably think we already know this, Mr. V, but just in case. Here we go. Okay, so I got the 0.5 times the 1.1 E3. Remember, the E button is right here, right there. Okay, on the TI, I got a TI-83 here, you can see. So TI-83, the E button is double E right above the comma. So that would be this one right here. Double E, you can just, it's kind of blurry, sorry. So, so you'd go second double E. Okay, why you do that, that's now scientific notation, and your calculator treats that like one number. Come on, focus. So 0.5 times 1.1 times 10 to the 3. Okay, and then we go times. Now, I've told you guys that that is the 6.9. So if I just hit the up button, see, up button, okay, and I just keep scrolling until I find that 6.94. That was one of, oh, that's it. That's the 25 kilometers, so equals. Okay, so 6 point, and see, it just brings down all those decimals, so you don't have to write them. Plus, okay, so the next one was half, or 0.5 times 1.3 E3. Okay, times, now this one is the 4.2, so I just scroll up to the 4.166, hit enter, see it brings those down, hit squared. Remember, you don't even need the negative. Oops, I think I messed up here. Times 10.5 times 1.3. Yeah, I need a times in there. Okay, times that, hit enter. Oops. Oh, I don't need that guy. Oh, sorry, my thing turned off on me. 1.3 times 10 to the 3. Here, we'll turn that on again. There, I think I got it now. Okay, so 0.5 times 1.3 times 10 to the 3 times, there we go, see I put my multiply in the wrong place, 4.1666666, okay, squared. Okay, hit enter on that. Oh, look. Okay, so that's what my calculator says, so I got to turn that into scientific notation. So that's 3.8 times 10 to the 4. 3.8 times 10 to the 4. Okay, so let's go back to here. Wow, that was intense, eh? So 3.8 times 10 to the 4 joules. Okay, that's cool. Now, for that second part, I'm just going to, I won't bother showing you on this one. So 0.5 times 2.4 E3 times 0.925 squared. So that is only 1,028 joules. So to sig digs, that's 1.0 times 10 to the 3 joules. Now look, 10 to the 3, 10 to the 4, that is clearly not the same thing. Okay, so that is how you show that this is an inelastic collision. So this collision is inelastic. Wow, that is crazy. Okay, that's what you have to do. So if you don't have one of these calculators, then I will, like I say, I will show you how to deal with that next time. But again, this is more of a physics 20 thing, all those numbers, but that's all right. Okay, so number 3, explosion. Wow. Hopefully you guys, you know that if you're getting bored or whatever, you can hit pause. Okay, go have a break and then come back to this, because I know this has been long. And trust me, the next one's going to be longer, so sorry. Okay, anyways, carry on. This is the last one for this section, so yay. Last one, second last one, I think. Let's just double check here. Yep, it is the second last one, because we got a little more to do here. All right, so let's talk about explosions. Okay, so in any kind of an explosion, something is sitting there at the beginning, and then it blows up into different parts. Okay, so the classic one is a gun, but there are other types. Okay, if you're in space, or an astronaut, and you throw something, okay, you provide a momentum forward to the thing you threw, and you have a momentum backwards. Okay, in this case, a 0.05 kilogram bullet is fired from a 5 kilogram gun. If the velocity of the bullet is 275 meters per second, what is the recoil velocity or kickback of the gun? Hopefully you guys have, maybe some of you have shot a gun before. If you shoot a gun, the gun kicks back on you. Okay, so you want to make sure that the stock of the gun is right on your shoulder, otherwise it'll kind of punch you and it hurts. So anyways, here's how we do this. we start off with P before equals P after. Okay, pretty common. Like we've been doing that a lot lately. Okay, now before the collision, the bullet's sitting there, the gun is sitting there. Like we don't even like they're kind of all in one big mass, so we could go M1 plus M2 if we really wanted. But what's the velocity of everything? Well, it's zero. So the momentum beforehand is just zero. I don't have to show any work for that. Everything's stopped. It's zero. Done. Okay, now afterwards though, I've got the mass of a bullet and it is moving at a velocity. Okay, then I have a mass of a gun. Here we can say MB and then MG if you really want. Okay, whatever. It's completely up to you. And then velocity 2 or velocity of the gun, it doesn't matter. Okay, now, so it's still 0. Okay, so the mass of the bullet, 0.050 kilograms. Okay, times the velocity of the bullet is 275 meters per second. Now, if you've ever shot a gun, okay, the bullet goes forward. So we can say that one's positive. Okay, so then we have the mass of the gun, 5.0 kilograms, times the velocity of the gun. Okay, that's interesting. So when we do the algebra on this, 0.05 times 275, okay, this works out to 13.75. Now, let's just ignore sig digs for a second. Okay, it's positive. So we would, to do the algebra on this, we minus 13.75. So minus 13.75. So 0 minus 13.5 is, 13.75 is negative 13.75. Okay, and that's kilograms, meters per second. Again, we kind of ignored sig digs because, again, you don't have to show me any of this algebra. You can just go formula, substitution, then down to the answer is all I need to see. But to show you guys, I should probably show you some of the intermediary steps. So 5.0 kilograms times V gun. So divided by 5.0 kilograms, divided by 5.0 kilograms. The kilograms are going to cancel. So negative 13.75 divided by 5 is negative 2.75 meters per second equals V gun. Now, of course, it's only 2 sig digs here with the 5.0 kilograms, so that would be negative 2.8 meters per second equals V gun. Okay, now, how we interpret that is if the bullet goes forward, the negative just means the gun goes backwards. So we can say that the V gun equals 2.8 meters per second backwards. And there is our answer. So yeah, 2.8 meters per second. Now remember the rules. You have to use all your digits, so 2.75. Okay, if you divide by 3.6, you get kilometers per hour to meters per second. So if you times by 3.6, you can go from meters per second to kilometers per hour. So that's 9.9 kilometers per hour. Okay, so if you have a gun on your shoulder and you go to shoot it, it'll kick back at just about 10 kilometers per hour, which is a pretty significant hit. Okay, and if you've ever shot one, like, you know that it can hurt if you don't hold the gun proper. Anyways, carrying on, because wow, we can get lost in a hurry if we're not careful. So anyways, velocity of the gun, 2.8 meters per second backwards. Okay, is the collision or explosion elastic or inelastic? Okay, well, let's think about this one for a second. I thought about removing this question, but you know what? You need to see this. So look, we solve this the same as anything before. So energy before equals energy after. Okay, what is the energy before? Guys, nothing is moving before. So the energy is all zero. Okay, and then 1/2 mv squared plus 1/2 mv squared, and this will be bullet, bullet, gun, gun. Okay, so let's talk really quick. How can we get energy from nothing? See, in this case, it seems like we're just creating energy, and it's silly. And so I really did want to discuss this with you, because what kind of energy does the bullet have, or the bullet gun system have, before you pull the trigger? Okay, remember, it has chemical potential energy in the form of the gunpowder. Okay, and when you ignite that gunpowder, that chemical potential energy turns into kinetic energy of both the bullet and the gun. So this, even though this is clearly inelastic, okay, you're not getting energy from nothing. You're getting energy from the stored potential energy from the gunpowder in the bullet. Okay, it's an important distinction. So, anyways, clearly inelastic. Okay, because they're all inelastic. There's lots of sound when you fire off a gun. Okay, but still, that's the idea. We don't have to show any work for this one, because clearly you start off with zero kinetic energy. Okay, and then you end up with lots of kinetic energy from the two things. So it's impossible that they'll ever be equal. Okay, however, where does that energy come from? The chemical potential energy of the gunpowder. Okay, thanks. All right, this is the last one. Now we've got to do a little bit of notes and backtracking a little bit. So, one type of inelastic collision occurs when two objects stick together after colliding. However, this type of interaction doesn't necessarily mean that the final kinetic energy of the system is zero. A good example of this is something called a ballistic pendulum. The type of pendulum used, this type of pendulum is used to determine the speed of a bullet. Okay, and we used this long before we had electronic timing devices. Like, we just didn't have a radar gun back in the day. So they still wanted to know how fast the bullet came out of the gun, and this is how they did it. Okay, so bullet is fired into the block, and then both the block and the bullet move up together as a group after the impact. The pendulum consists of a stationary block of wood suspended from the ceiling by light ropes or cables. Okay, when a bullet is fired at the block, the bullet sticks in or becomes embedded in the wood upon impact. The kinetic energy of the bullet is converted to sound and thermal energy, deformation of the wood in the bullet, and the kinetic energy of the pendulum bullet system. The initial momentum of the bullet causes the pendulum to move. But since the pendulum is suspended by cables, it just swings upward just after the bullet becomes embedded in the block. As the pendulum swings upward, okay, all that kinetic energy gets converted into gravitational potential energy. So the EK turns into EP. Now, remember from back in Physics 20, EK is 1/2 mv squared, and the gravitational potential energy is mgh. So doing that, if I know the height that the pendulum moves upward, I can figure out the velocity at which the bullet and block moved. Okay? By using the conservation of energy, it's possible to determine the speed of the bullet pendulum system immediately after impact, and then I can apply conservation of momentum to determine the speed of the bullet. Okay, so let's give this a try, because this is how they did it back in the day, and it is ingenious. Okay, so an example of a ballistic pendulum. Okay, a 0.0149 kilogram bullet is fired from a pistol, strikes a 2.0000 kilogram ballistic pendulum. Now, they put that many sig digs on so that we can subtract or add the two masses later on. Okay? Upon impact, the pendulum swings forward and rises to a height of 0.219 meters. So just about 22 centimeters. Okay, what is the velocity of the bullet immediately before impact? Okay, well there's some things we got to do here first. Okay, we know that the ballistic pendulum had a kinetic energy after the bullet hit it. Okay, and that kinetic energy turns into potential energy. So we go 1/2 mv squared equals 1/2 That's funny. Equals mgh. Now, what's really brilliant about this part is because there's two m's on each side, the masses can cancel. Okay, so we get 1/2 times the v squared equals g. Now on Earth, that's 9.81 meters per second squared, times the height, which is 0.219 meters. Okay, so we can divide by 1/2 or times by 2, depending on how you were taught. Okay, and then square root. Okay, so 9.81 times 0.219 times by 2 or divide 1/2. Okay, hit enter on your calculator. That's 4.30 meters squared per second squared. And then square root to get a velocity of 2.07, 3 sig digs, meters per second. Okay, now of course that is forwards, obviously. Okay, because that is the direction that a bullet goes. Okay, awesome. So that is the velocity of the bullet pendulum system. Now let's apply the momentum stuff. Remember, the momentum before a collision has to be the momentum after a collision. Okay, so let's ponder this for a minute. Remember, before the collision, there is a bullet and a stationary block of wood. Okay, so I've got a bullet, mass of the bullet times the velocity of the bullet, plus a stationary block of wood. So we have the ballistic pendulum. So I've got the mass of the pendulum times the velocity of the pendulum. Now, funny thing, before the impact, the ballistic pendulum is just sitting there. It has no velocity. So remember, the momentum of that is going to be 0 because the velocity is 0. Brilliant. Okay, after the collision, we've got the bullet sticks into the pendulum. So we've got a mass 1 plus a mass 2, and we know its velocity because it moves off at some new velocity. Velocity of the pendulum. So now let's put in our numbers. The mass of the bullet, 149 kilograms, times the velocity of the bullet, which we don't know, plus 0. So this is why there's so many sig digs, because this is going to be 2.0149 kilograms. Okay, they wanted to make sure that we had that many there. And then the velocity of the pendulum, well, that's what we just figured out there, 2.07 meters per second. Now remember, it's not 2.07, there's more to it than that, right? So you have to carry down all those decimals. Okay, so scroll up, get them all, or just type them all, because it should still be on your calculator. Okay, so type them all, not a big deal. Okay, and then divide by 0.0149. Divide by 0.0149, and the velocity of the bullet, okay, and that's kilograms, so the kilograms cancel, so our units are meters per second, and it works out to 280 meters per second. Now, of course, the bullet is going forwards, so we can just get away with that. So the velocity of the bullet is 280 meters per second forward. Wow. Now, look, guys, I know this was intense. I know the video was long. Sorry, next one is going to be longer, so brace yourself for that. But before you do that, you have to do these questions, because this stuff, you need to master the one-dimensional stuff before you even try the two-dimensional stuff. So it is page 486 in your textbook, 3, 6, 8, and 10. Okay, section 9.3, and we go from there. So guys, good luck. See you next section.